to all. So today I will be finishing the module number 1. I have a particular agenda for today's class. We will complete the remaining slides of this particular module, and also we'll solve a couple of numericals that we usually come across in fundamentals of heat transfer, the fundamental and basic application of heat transfer and concepts and the governing equation. So until the last class, what we have seen is the laws proposed by certain researchers, certain scientists during the olden days, and those laws were applicable to quantify, to calculate what will be the rate of heat transfer when there is conduction, when there is convection, and when there is radiation. So we have seen that in the conduction equation proposed by the Fourier law of conduction, there is a constant, it's not a constant actually, there is a property called as a thermal conductivity, which plays a major role, and that thermal conductivity is a property, depends on the materials. Similarly, in convection, we have seen that there is something called as a heat transfer coefficient, which plays a major role, and then it is not a property. So understand the difference between the thermal conductivity and the heat transfer coefficient. Conductivity is a property, whereas the heat transfer coefficient is not a property. It depends on various factors. So the entire problem of convection heat transfer is to determine the value of the heat transfer coefficient. And finally, coming to radiation, we have seen that the radiation depends on the temperature differences, but those temperatures are raised to the power of 4, which means the radiation heat transfer is actually a non-linear phenomenon. So as the temperature changes, temperature increases, the rate of heat transfer also increases rapidly. So that gives us a certain understanding of when we should consider radiation and when we can ignore radiation and so on. So you will understand these things later on as we move on. So now we will come to the last part of the module slides, and I will complete that. So in the previous class, we have seen how property values are coming into equations and how to linearize the radiation rate equation. Also, what are the different values of emissivity. We have ended with how the first law of thermodynamics and the second law of thermodynamics are connected to this particular subject of heat transfer. Okay. So this is what we have seen. Now moving on, we'll see what this topic called as identifying the modes of heat transfer, are also called as the system identification. So why this is important is because many a times, in fact, every time whenever you deal with a heat transfer problem, you will have to decide which equation to apply. You have seen 3 equations, one for conduction, one for convection, and one for radiation. Which equation to apply is not known to you. So how do we know which equation to apply? That depends on how well you identify the mode of convection taking place. And in most real life situations, all the 3 modes of heat transfer will come into picture. Sometimes you may have to simplify those things. Sometimes you may have to make some assumptions, ignore certain things. So in such situations, you will be first, you should be able to identify the mode of heat transfer, and then you should be able to roughly tell which is more dominant and which is less dominant, and just consider the more dominant one, ignore the less dominant one, so that you will gain by experience. So in today's class, I will take up these 3 problems and I will show you what will be the modes of heat transfer. Now the first example is a hot coffee in a flask. So this is a thermos flask. So the purpose of thermos flask is to keep cold fluids cold or hot fluids hot inside this particular vessel, inside this container. Now the way in which we do is to isolate this particular contents of this container from the surroundings. So ideally this particular container must have no contacts with the surroundings, no physical contact. In fact, ideally if it is inside a vacuum, it will be ideal, it will have the least amount of heat transfer either from the vessel to the atmosphere or from the atmosphere to the vessel. But it is difficult to provide vacuum, and it's also difficult to provide or it is difficult to maintain zero contact. At some point there will be contact, and that point will be the place where heat transfer can take place. So here you see such a situation here. This is the vessel which contains the cold contents or the hot contents, cold fluid or the hot fluid, and this must be kept cold or hot by isolating from the surroundings. This is surrounded by an external cover. External cover is one level of shield or one level of protection from the heat transfer. In between this vessel and the external cover, there is a gap. This gap, ideally, if it is vacuum, if it is a perfect vacuum, then the heat transfer, heat losses will be minimal. But it is difficult to maintain a vacuum. There will always be some air ingress into it. Therefore, this is filled with a low thermal conductivity medium, and the cheapest low thermal conductivity medium that we have is air. So we allow air to occupy this space. So air is a poor conductor, but you see there is some contact here. There is a contact with this, and from here there can be heat conduction to the surroundings. We shall see all those things. We will focus on this part. Okay, we'll focus on this cross section alone, and we will ignore this part. This is a small region, and the amount of area of contact is very negligible. We know that heat transfer is area dependent. So higher the area, higher will be the heat transfer. The area is low here, therefore the amount of heat transfer here will also be low. So we will ignore that. We consider only this part. Now this cross section is shown here, is enlarged, magnified, and shown here. Okay. Now this is the wall of the cover. This is the cover, and this is magnified and shown here. So sorry, this is the wall of this vessel. Okay. So inside this there is hot coffee, and outside here there is air. So across this wall we have hot coffee on one side and air on the other side. Hot coffee is warmer than the air, therefore the heat transfer will be in this direction from high temperature to low temperature. Now we should be able to tell what will be the mode of heat transfer, so that we should be able to apply which of the three equations that we have seen. Now inside there is coffee. Coffee is a fluid, a liquid, and whenever there is a fluid, the mode of heat transfer will be a combination of convection and conduction, but predominantly convection. So in the inside we can treat this as a heat convection. Now across the wall of this flask inside, it's a solid surface. Therefore, the only possibility or the predominant possibility is heat conduction. So heat will be conducted from the inside wall to the outside wall. And the temperatures across this inside and outside wall will be different. Therefore, Q2 will be conducted. And from here, heat has to reach the other side across this airspace. So there is airspace here. This is the airspace. This heat has to cross this. Now, one way of crossing this is direct jump from this surface is at a temperature higher than this surface. Therefore, there is a direct jump possible, which means this Q5 you see here, this can be radiation. And then you see there is also Q3 and Q4. This Q3 is the convection between this surface and the airspace, and Q4 is also convection from the airspace to this wall. That means the heat transfer from this wall to this wall is taking place by a combination of radiation and by convection. So that thing you need to consider. Once the heat reaches this wall, that is the inside of this cover, the outside of the cover is exposed to the ambient air, the room air. Therefore, there is a temperature difference. So, the heat will conduct from this point to this point. So, across this wall, on the inside there is convection and outside there is convection. And if this particular vessel, this flask is in a large room, like it is always is, then there will also be radiation heat transfer. There is a direct jump you see from this point to this point. So, this is radiation heat transfer and this is the convective heat transfer. Okay, so wherever there is a fluid here, there is a convection, there is a possibility of radiation. Wherever there is a solid surface, the predominant way of heat transfer is conduction. So in this way, you will have to choose and appropriately use the necessary equations. Then here is another example. We see there is a fireplace in a room. So in cold countries or regions which are cold, the fireplace is kept so as to protect the room from the harsh winters. So there is a fireplace maintained, and you see this fire is burning here, and all the product gases are allowed to leave. These product gases sometimes can be poisonous and can be harmful. Therefore, we don't want these product gases to enter this room. So gases should not enter, but the heat from this flame should enter this room. Now, how does this heat enter this room? It is actually, there is a partition here, you see, there's a partition here, and therefore we have no way the gases can cross this fireplace into this room. But since there is a flame here at a higher temperature, flame temperatures are usually about 1500 degrees Celsius, and the room temperature is to be maintained at a comfortable 25 degrees Celsius. Therefore, for heat to follow, there is a temperature difference prevailing here. Therefore, heat will flow, but how will it flow? So, since there is a high temperature flame, there will be radiation from this point to this point. So from the flame to the inside wall of this partition, there will be radiation. And also this region is not vacuum. This region is having certain gases. So these gases will undergo some convection, and therefore there is a convective heat transfer also from this point to the inside wall. And from the inside wall to the outside, that means from here to here, there should be heat transfer possible. So that heat transfer is in the form of predominantly convection. But another provision is also made in
through the glass plate there should be conduction, right?
Through this, yes, through this glass plate there is conduction, but this plate, as you see here, this is enlarged version. There is an air flow. See here, there is air flow. So air is deliberately made to flow through this glass plate. There is an empty space, so air will pick up the heat, and the hot air is actually coming out. Okay, so in this way there is a convection, mostly convection in this region because there is a continuous supply of air. Okay, so there is conduction, there is radiation from the fireplace to this wall, there is a conduction across this wall, and inside there is convection, and on this, from this region to this wall there is convection, then across this wall there is conduction, and from this wall to outside there is a convection because there is a room air, and also there is radiation because there is a temperature difference. Okay, and also there is this internal channel is provided with the circulation of air so that air actually receives heat from across this and comes out. Okay. So in this way, various modes of heat transfer are utilized in keeping a fireplace inside the room. Coming to the third example, this is a thermocouple junction. Thermocouple junctions are used to measure the temperature of any object. So how will the temperature be measured? Just like our mercury in glass thermometer, the bulb which carries the mercury is subjected to the required subjected to the heat transfer of the body which is supposed to be hot or cold. So what happens is after placing this thermocouple bead, see, you see this here, this is called as the thermocouple bead. Okay, this is the one equivalent to the mercury bulb in a mercury in glass heat, thermometer. So this particular bead is supposed to come into contact with the surface which whose temperature we need to measure. And once there is a thermal equilibrium between those two surfaces, that means this thermocouple bead and the surface whose temperature needs to be measured, the thermal equilibrium has been reached, and whatever reading this thermocouple will give us will be the temperature of that particular surface. The working of the thermocouple, I am not sure if you have already known, but what is there in the thermocouple is there will be two wires of different materials. These two, you see here, there is one wire here, another wire here. These two are welded at this point called as the thermocouple bead. Even though in this figure, this thermocouple bead is shown to be a large, like a 1 centimeter diameter, it's actually a fraction of a millimeter. A very, very small one, a fraction of a millimeter, so that it quickly absorbs the heat and increases its temperature. Now, the bead of this thermocouple is at one temperature, and the other two wires that are extensions, they are at a different temperature. So, the temperature difference between this end, so thermocouple will have two ends, one hot end and other one cold junction. Here, this is the cold junction. These two will be at different temperatures, and this difference in temperatures will drive an electric potential. So thermocouples are usually coming along with the voltage measurement device. So this voltage is measured, and the difference in the voltage is proportional to the temperature difference. So the measurement of voltage will be an indicator of the temperature of this surface. So the requirement for a thermocouple or operation is that its bead should be in contact with the surface or with the fluid whose temperature is being measured. Okay, now in this particular example, we are trying to measure the temperature of a hot solid here. We are not trying to measure the temperature of a hot flowing gases. So hot solid. So what is there? We have something called as this thermocouple well or thermo well. Into this thermo well, we introduce this particular bead. So heat is conducted from the hot surface across the thermo well towards the bead of the thermocouple. So there will be heat conduction here, and on the other side, the temperature is low. Why is the temperature low here? Because it is not, this junction is not exposed to the hot side, and also there will be cooler gases here. So there is a temperature difference maintained. So there is conduction in this across the bead, and on the other junction, cold junction, there is a convection. So because of this temperature difference, we have heat, we have a voltage difference. So if you try to measure the voltage across these two surfaces, or these two beads, or these two junctions as they are called, we will note some voltage, and that voltage will tell us what is the rate of, what is the temperature. Okay. So this is how you need to identify, depending on, there are many more problems. You take any standard textbook, you will have these situations. System identification in itself is important, because only once you identify it correctly, you will be able to apply the appropriate equations. So in that way, you should be gaining experience and gaining confidence whenever you try to solve a problem on heat transfer. Okay. So that's an advanced application. As far as we are considered in this particular course, what happens is when we are dealing with a chapter on conduction, most of the problems will be conduction related problems. When we take up the chapter on convection, most of the problems will be convection related problems. Likewise in radiation also. So as long as you're studying and solving problems here, the things will be quite obvious and quite clear. But when you go into applications in real life, you will have to sit and think about what all heat transfer processes phenomena can take place, what are all possible, and incorporate those things in framing the equations and subsequently solving those equations. Okay. Now we'll take up some problems related to heat transfer, some application, fundamental problems related to this particular chapter. So, yeah.
So you mentioned that air is not a good conductor of heat. In that case, when we blow on something, how come the air takes away the heat?
By convection.
Okay, so in that case, it can cool faster.
Yeah. Okay, so let me create some new slide here. All right, so I will take up a problem and solve it. So look at the problem, we'll read it. The wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during steady state operation reveal temperatures of 1400 and 1150 Kelvin at the inner and outer surfaces respectively.
Excuse me, sir.
Yes?
Sir, you are not sharing the screen.
Yes.
Am I not audible?
Not
You're not
sharing the screen, sir.
I think I didn't share that problem. Yeah. So we have a wall of an industrial furnace. Industrial furnaces are used to melt certain metals. That's one application. So inside of the furnace is hot compared to the outside. So the wall of the furnace is supposed to withstand these high temperatures. For that, they use something called as the fire clay bricks. So this is the one which comes into direct contact with the hot gases and also the metal. So this fire clay brick has a thermal conductivity of 1.7. So this is a low thermal conductivity. 1.7 is a low thermal conductivity. That means this fire clay brick is a poor conductor. So measurements made during the steady state operation reveal temperatures of 1400 and 1150 Kelvin at the inner and outer surfaces respectively. So what is the rate of the heat loss through the wall? That is 0.5 meters and 1.2 meters on a side. So this is the problem. So we are given a wall of a furnace and the temperatures on the either side of the wall and also the area, the dimensions of the wall, which means the height, width, and also the thickness. The conductivity also is given. We are asked to find the heat loss through the wall. Okay, so this is a very direct problem, application of heat transfer. So this is, let us say, this is the two-dimensional representation of the furnace. This is the, let us say, hot metal, and this is the wall we are talking about. So we are interested in finding out what is the rate of heat transfer across this wall. So this is the inner side of the furnace and this is the outer side. So this is ambient. So this is the wall we are interested in. So I will try to draw the wall here. I'm not very comfortable using this digital pen, so I'm not able to draw straight lines. So imagine that this is a rectangular wall. This wall has got a thickness of 0.15 meter, and this side is at 1400 Kelvin. So here temperature is 1400 Kelvin, and the temperature is 1150 Kelvin. Right, it is. Now, since this side is warmer than the other side, the heat is supposed to travel across in this direction. This is so, and obviously, on the inside there are gases, hot gases. On the outside there is air. So from these gases to this wall, there will be heat convection. From this wall to the air, there will be heat convection. But the question asked is, what will be the heat transfer across this wall? And we are also given all the data necessary for finding out the heat conducted across this wall. We are also given the value of K. K is 1.7 watt per meter Kelvin. So using this, we can try to find out the heat transfer. Okay. So we are also given the area of this wall 0.5 meters by 1.2 meters. 1.2 meters is the height, and the depth if we measure it is 0.5 meters. So using the information, we can first find out what is the mode of heat transfer. So across this wall alone, we say the mode of heat transfer is conduction only. So the heat transferred across the wall is equal to heat conducted is equal to the Fourier law of heat conduction is minus Ka dt divided by dx. So if we measure x in this direction, x is 0 here, we measure x in this direction, then the heat conducted will be minus k is 1.7, so minus 1.7 multiplied by the area is 0.5 multiplied by 1.2 multiplied by dt. In the positive direction, the temperature change is 1150 minus 1400 divided by dx. dx is nothing but the thickness, which is 0.15. So if you calculate that value, you will get the rate of heat transferred across the wall, which is nothing but the rate of conduction across the wall. So calculate that value and tell me how much you get.
$1,700, sir.
1700. So 1700 watts. So all these three equations, rate equations, the Fourier's law, Newton's law of cooling, and Stephan-Boltzmann law, they give the rate of heat transfer in joules per second or in watts. So this is the amount of heat transfer. Now you see here, we wrote the heat conduction equation in the most fundamental way. See, included the negative sign here, and this negative sign was cancelled by this negative value obtained by subtracting 1150 minus 1400. This I explained to you. This negative sign is deliberately introduced to counter the negative value of this derivative in the direction of heat transfer. But over a period of time, you will see that this, once you understand the physics of conduction, you will see that this negative sign is not really important for you. So what you can do is you can ignore that. You can say Q is equal to Ka delta T by delta X, because now you know heat transfer takes place from high temperature to low temperature. So what you can do is this is 1.7 multiplied by 0.5 multiplied by 1.2 multiplied by 1400 minus 1150 divided by 0. Which will again give you 1700 watts. So in this way, you can actually get rid of the negative sign, but it is a good practice, and some purists will actually prefer to have this negative sign because it avoids any mistakes in complicated problems. Okay, so in this way we can solve this problem. We'll take a similar problem. A wall has an inner and outer surface temperatures of 16 and 6 degrees Celsius respectively. The interior and exterior air temperatures are 20 degrees Celsius and 5 degrees Celsius respectively. The inner and outer convection heat transfer coefficients are 5 and 20 watt per meter square Kelvin respectively. Calculate the heat flux from the interior air to the wall, from the wall to the exterior air, and from the wall to the interior air. Is the wall under steady state condition. Okay, so here we have a problem, similar problem. There is a wall, it is having different temperatures across, and also it is having different convection coefficients uh, because of convection coefficients at the inside and outside. Okay, so because of this, we will have to find out what is the heat flux. Now, in this problem, we are asked to find heat flux, whereas in the previous problem, we are asked to find the rate of heat loss. So rate of heat loss or rate of heat transfer has the units of watts. So we found out the rate of heat transfer as 1700 watts. Now in this problem, find the heat flux. Heat flux is a quantity which is having the units of watt per meter square. So it's a quantity which can take any value irrespective of the area. So you divide the heat transfer with the area and you get what is this heat flux. So this is nothing but the rate of heat transfer per unit area. That's the meaning. Okay. So let us try to solve this problem. All right. So first I will draw this wall. So this is the wall, vertical wall across which heat transfer is taking place. Okay. Now this wall has inner and outer surface temperature of 16 and 6. Say this is inside, this is outside. So this is 15 degrees Celsius and this is 6 degrees Celsius. The interior and exterior air temperatures are 20 and 5 degrees Celsius respectively. Now the air on this side is 20 degrees Celsius and air on this side is 5 degrees Celsius. So see the difference. The wall is at 16 degrees Celsius, but inside air is at 20 degrees Celsius. So there is a temperature difference between the medium and the wall here. Likewise, there is a temperature difference between this wall and the medium here. The inner and outer convection heat transfer coefficients are 5 and 20 watt per meter square Kelvin. So H is 5 and H is 20. The unit is watt per meter square Kelvin, which is also same as a watt per meter square degrees Celsius. So 1 Kelvin is equal to 1 degree Celsius. So even though your heat transfer coefficient units are given in watt per meter square Kelvin, it can also be written as watt per meter square Celsius and vice versa. So do not get confused if the units are changed. Now, calculate the heat flux from the interior air to the wall. What is to be calculated is interior air to the wall, the heat flux. So heat flux is represented as a Q prime. Then find from the wall to the exterior air. So this is how much? This is how much? From the wall to the interior air. From the wall to the interior air. So this is how much? So this is the third question. And one final question is the wall under steady state condition? So we have to find out. Now, to tell whether the wall is in a steady state condition, the condition should be that whatever heat is entering should leave. So for steady conditions, there should not be change in things. There should not be any accumulation. The flow should be continuous. So whatever is entering, if it is leaving, then the system is under steady condition. So that we should check. Okay, so first we'll calculate the heat transfer from inside to wall. This is the inside. It has got an ambient atmosphere and also heat transfer coefficient. So the moment heat transfer coefficient is given, it implies that there is a convection involved. So heat convected from this to this wall we should find out. That will be H A delta T. So this is the formula we have seen. Delta T is the temperature difference which is driving the heat transfer. Now we have to find the heat flux. So Q prime in to wall. So we can remove this, or per area can be 1. Then this H delta T. So H is 5 multiplied by delta T is 620 minus 16. So 5 into 4 is 20 watt per meter square. So this is the rate of heat transfer. So this we just calculated. This is 20 watt per meter square. Okay. The next question is, what is this value from the wall to the outside? So Q prime from wall to outside. Again, there is convection, so H delta T. Except now the H value is different. H is outside, H is given as 20. So this is 20 multiplied by delta T. This wall is at 6 degrees Celsius and this temperature, ambient temperature, is at 5. So 6 minus 5. So this is 20 watt per meter square. And the third question is, what is the rate of heat transfer from the wall to the ambient? So what we calculated here is from the ambient, inside ambient to the wall. Now we are asked to calculate what is the rate of heat transfer from the wall to the ambient on the inside. So I'll write that here, Q prime wall to inside. Again the formula is H multiplied by delta T, but now H is 5, same as this value. Delta T is 16 minus 20, because the direction is changed now. 16 minus 20. So 16 minus 20, so this will be minus 20 watt per meter square. So you see here, this is 20 and this is minus 20. So the minus indicates that what we assumed, the heat transfer assumed, is from one is actually the opposite of the actual heat transfer. So that is the meaning. Okay. So we are asked to find out three answers. The first one is heat transfer from the inside to the wall, from the wall to the outside, and also from the wall to the inside. So for these three, we calculated each one. This was 20, this was 20, and this is minus 20. Now one last question that is asked is the wall under steady state condition? Steady state condition. So for steady state condition to be maintained, we have to see that the amount of heat entering should be same as the amount of heat leaving. So we saw that this is the amount of heat entering and 20 watts is the amount of 20 watt per meter square is the amount of heat flux leaving. See, for steady state conditions, it's the heat which should be same, not the heat flux, because heat flux depends on the area. But since this is a rectangular wall, when we said it is a wall is always rectangular unless it is mentioned. It can be, sometimes it can be the wall of a spherical container, but unless it is mentioned, take it as a rectangular wall. A rectangular wall, inside area and outside area should be the same. So since the heat fluxes are same, heat flux inside to wall is equal to heat flux from wall to outside. So heat flux multiplied by area, this is inside to wall, is equal to heat flux multiplied by area from wall to outside. Since the areas are same, this and this will get cancelled. So heat transferred, heat into wall is equal to heat transfer from wall to outside. So this equation means that whatever is entering is leaving. There is no accumulation. If there is accumulation, the amount of heat transfer entering will not be same as the amount of heat transfer leaving. So since there is no accumulation, the system, the wall is in steady state. So that is something we can infer. Okay. Take up another problem. Now this problem is a conjugate heat transfer problem. So what is a conjugate heat transfer problem means that it involves more than one mode of heat transfer. Okay. So let us see this problem. Yes?
Sir, I just have one doubt in the last question, sir.
Yeah.
Sir, in that, like, according to formula, it's T surface minus T air, no, sir? Like, so shouldn't it be 16 minus 20 in the first case? And then in the last case, 20 minus 16?
No. See, in convection heat transfer formula, the Newton's law of cooling, it is not delta T. It's not dt. Okay. It's the temperature difference. dt is kind of a vector. It's always final minus initial. Whereas the delta T is the positive temperature difference which is driving the heat transfer.
Okay, sir. Okay, sir.
So here we have an overheated 30-meter long uninsulated steam pipe of 120 millimeter diameter is routed through a building whose walls and air are at 30 degrees Celsius. Pressurized steam maintains a pipe surface temperature of 150 degrees Celsius and the coefficient associated with natural convection is H is equal to 10 watts. The surface emissivity is 0.8. What is the rate of heat loss from the steam line? Okay, so we have a hot steam pipe and it is undergoing heat transfer. We have to find out what is the rate of heat loss.
So,
Yes.
so in the previous question, it said from the interior wall and the interior air and the wall and interior air. So why will the heat go in two directions? Will it not take only the net direction of whichever is higher minus lower in terms of temperature?
It will. Yeah, so you're right. Since in this case we know the temperatures, we are very clear about the direction of the heat transfer. Sometimes when we are not clear of the direction of the temperature magnitudes, we may have to decide which way the heat transfer goes. So in the previous problem, there is only one way in which the heat transfer goes from the inside to the wall and not the other way, because wall is cooler than the ambient.
Okay, sir.
So that question is only to mislead you.
Okay, sir.
All right. So here I will draw a schematic. Here we have a pipe, and this pipe is enclosed in a building, in a huge building. Okay. Certain conditions are given. So there is a steam passing through this pipe. Overheated 30-meter long. 120 millimeters. So phi is 120. Building whose walls and air are at a 30 degrees Celsius temperature. So this wall is at 30 degrees Celsius. This ambient air also is 30 degrees Celsius. Pressurized steam maintains the pipe surface temperature of 150 degrees Celsius. This temperature is 150 degrees Celsius. That is ES. Surface temperature is 150 degrees Celsius. And the coefficient associated with natural convection is H is equal to 10 watt per meter square. So H is equal to 10. The surface emissivity also is given. So emissivity is 0.8. So emissivity of the pipe surface. What is the rate of heat loss from the steam line? So this is the question asked. So to answer this question, first we should identify what are the modes of heat transfer in this case. So as you can see here, there is steam flowing. So inside there is convection, but we are not asked to find out what is the rate of heat transfer from the steam to the wall. We are asked to find out what is the heat loss from the wall to the surroundings. What is the rate of heat loss from the steam line? So we know the surface temperature of this steam pipe. We know the heat transfer coefficient, and we also know some radiation data. So sometimes the data itself will be an indicator of what are the modes of heat transfer. So in this particular case, no thermal conductivities are given. We are given the heat transfer coefficient and the emissivity data, which implies that there is a convection involved and there is a radiation also involved. But sometimes some extra data can also be given to mislead you. So don't fall for that prey. But as far as this particular problem is concerned, it is true that convection and radiation is involved. There is no conduction involved. There is conduction involved across the steam pipe. There is conduction involved, but we are not asked any question related to the heat transfer across the steam pipe wall, or what is the temperature difference across the steam pipe wall. So we are not bothered about conduction in this particular problem. Okay, so I'll write down the data. We are given the surface temperature as 150 degrees Celsius. Since radiation is involved now, it's always better to convert to Kelvin. So 150 degrees Celsius, when you convert it to Kelvin, will be 423 Kelvin. Similarly, T infinity is 30 degrees Celsius, which is 303 Kelvin. So the heat transferred is equal to heat convected plus heat radiated. So we'll calculate the heat transfer. Heat convected is H A delta T plus heat radiated is epsilon sigma A Ts power 4 minus T infinity power 4. Okay, so now we'll substitute the data. H is 10 multiplied by the area. Now area of the wall of the pipe surface. So area is pipe surface, not pi r square, it's pi d. Yeah. So pi multiplied by diameter is 120 millimeters is 0.12 meters multiplied by L is 30. So this is pi multiplied by 0.12 multiplied by 30. This is the heat convected plus heat radiated will be epsilon 0.8 multiplied by sigma. Stephen Boltzmann constant is 5.67 multiplied by 10 power minus 8 multiplied by area, again is the same area as per convection. Pi multiplied by 0.12 multiplied by 30 is multiplied by T surface is, oh sorry, here I didn't multiply the surface with the temperature difference. So this is 423 minus 303. This is for convection. And for conduction, sorry, for radiation, it is 423 power 4 minus 303 power 4. So you should evaluate this, and if you evaluate that, you will get the value as 25.6 kilowatt, 25.7 kilowatt. So whatever individual terms, if you evaluate, you will evaluate this separately and this other radiation heat transfer separately, you will get in watts. So you will get large numbers. So when you convert that, you will have this. When you add them, you will get a huge quantity, which is equal to 25.7 kilowatts. So this is the amount of heat transfer across heat transfer from the wall surface, steam pipe surface to the surroundings. Okay. So this is one problem involving conjugate heat transfer or different types of heat transfer. All right. So I will stop at this because the time is up. and we'll continue in the next class. So tomorrow we'll meet again. I will start a new module, but before that I will also solve one problem which involves some mathematics. So that will be helpful to you. Okay. Now let me quickly take your attendance. Mrutunidhi?
Present, sir. Rutunidhi present, sir.
Vilash?
Present, sir.
Dan Cherian?
Present, sir.
Pranav
Present,
Dilip?
sir.
Present, sir.
Sir Madhusudan present, sir.
Pranadili present, sir.
Siddharth?
Present, sir.
Vatsan?
Present, sir.
Yes, sir.
Palanivel? Lagan?
Present, sir. Trishant present, sir.
Present, sir.
Lagan?
Present, sir.
Niranjan?
Present, sir.
Vaibhav Karan?
Present, sir.
Vijit Menon?
Present, sir.
Praveen?
Present, sir. Adil.
Siddhi?
Present, sir.
Ayush Tripathi?
Present, sir.
Harshavardhan?
Sir, Hamza Hassan present, sir.
Vardhan?
Yes, sir.
Present, sir. Present, sir. Present, sir.
Pratap Singh?
Present, sir.
Vania?
Present, sir.
Sai Rohit?
Present, sir.
P. Raman?
Present, sir.
Deepesh?
Present, sir.
Venkat?
Sir, present, sir. Vishal.
Present, sir.
Kumaran?
Present, sir.
Sundar Krishna?
Present, sir.
Pranav?
Present, sir.
Jayanti?
Present, sir.
Niket?
Present, sir.
Badri Narayanan?
Present, sir.
Present, sir.
Present, sir.
Harish Raghav?
Present, sir.
Rahul?
Present, sir.
Bose?
Present, sir.
Har?
Present, sir.
Karthik?
Present, sir.
Present, sir.
Prakash?
Yes, sir.
Gita?
Present, sir.
Prem Kumar? Charan
Yes, sir.
Sarvesh?
Present, sir.
Charan Sarvesh?
Present, sir.
Okay. Prem Kumar? Charan
Yes,
Ajay?
sir.
Enold Simon?
Present, sir.
Vamsi Krishna?
Present, sir.
Venkatesh? Anakshaya?
Present, sir.
And Dev?
Present, sir.
Arun?
Present, sir.
Kunal Rao?
Kunal present, sir.
Vignesh Krishna? Vedant Madhur?
Present, sir.
Present, sir.
Swami?
Present, sir.
Vasan?
Present, sir.
Priyan?
Present, sir.
Narayanan?
Present, sir. Present, sir.
Raj,
Yes, sir.
Keshav Kumar,
Present, sir.
Ash Kumar, Karthik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Ahalya,
Present, sir.
Sarvesh Krishnan, Elsie Femina,
Present, sir.
Jafet Gianal,
Present, sir.
Amal Manoj.
Present, sir.
I'll call the absentees once again. Palanivel, Pratik Krishna,
Present, sir. Present, sir.
Praveen,
Sir,
Praveen
Praveen,
present.
he's replied in chat box.
Chaturvedi, Motishwar,
In chat box for Motishwar.
Prem Kumar,
Sir, in the chat box, sir. Prem Kumar.
Vignesh Krishna Madhukumar, Akash Kumar,
Sir, chat box. Sir.
Sarvesh Krishnan. All right.
Excuse me, sir.
Yeah.
Vignesh Krishna, sir.
What's your number?
19 BME 1274.
All right. So I'll stop the recording. You can leave the class now.